Thank you.
Okay, excellent. So we talked about what we just talked about, and now we can move on to talk about improve performance. So we have a number of algorithms. We have in the wild, there's a lot of more algorithms, learning methods. People think that because not any model can perform at the optimal level, maybe if we put in multiple methods together, the overall performance might improve. So this is ensemble method. So no matter your baseline methods, learning algorithms can be anything. Ensemble methods basically treat those individual methods as weak learners or base learners, and then they harvest the result from those different models to try to predict, to improve the prediction accuracy. So popular ensemble methods, we're going to introduce bagging, boosting, and random forest. Random forest is based on the decision tree. I should mention that decision tree algorithms are in general performing well, and they are in general rather robust. But rarely in real applications, people would use a single decision tree. Random forest is very popular for that reason. Whenever you need a decision tree, it's most likely you're going to use random forest. It's precisely because random forest provide more robust prediction. So we're going to start with bagging. The idea of bagging is very simple. That the idea is just to have multiple systems classify or predict anything, then we take the average for the regression problem, numerical prediction, or we take the majority of the vote for classification problem. So the training process, you bootstrap, you sample with replacement. Then you generate multiple training set, and then you can learn multiple classifier models. So in the slides, we're talking about classifier models, but you can always replace it with numerical prediction models or regression model. The idea is very similar. Then at the classification step or the prediction step, you will classify this unknown sample. This M model is going to return different predictions, and you count the vote, and you take the majority vote. That's how we do the classification or prediction. For numerical prediction, you just average the value. In general, ensemble methods performs at more robust level. The performance may or may not improve, may not improve a lot, but definitely they're more robust. Boosting idea, I see it as an improvement over the first method, where we consider the performance of the different models. So boosting will start by assigning weights to each training example. It says my internet connection is unstable. Oh gosh. Then we can learn K classifiers. So we first, using this first classifier, train the first classifier, and use this classifier to train, to predict. And then for the triple, for the observations that's been predicted wrong, we will update the weight of that training example. And the next round, when we sample the training examples, we're going to give more weight. We will sample based on the weight. So those difficult examples going to have a higher chance to be sampled. Eventually we trained K classifiers. The final model combines the vote from each of the classifiers, where the weight of each classifier's vote is a function of its accuracy. So I think we have example here. So the model arrow. So the idea is to sample with replacement, but every time our sampling going to cover more difficult cases that has not been classified correctly by the previous classifier. So our model, the error rate is the missed classification. This is weight, 1 or 0. If there is a, this basically counts how many errors this classifier make. Then with the error, then we can weight this classifier's vote. So our idea is we want to trust the modifiers, the classifiers that has lower, smaller number of errors. Question? Okay.
Will this result in overfitting?
No, I don't think so. Yeah, but no. I see your overfitting argument is because you focused on the harder examples, right? So your later classifier more and more focused on the harder examples. However, you did not change the algorithm.
I would argue that it does not lead to overfitting because each of those classifiers is trained based on a set of the data, not all of the data.
Does that make sense?
Thank you.
It is, yeah, I agree, because we always sampled the same amount of data and do the ensemble. It should not create overfitting problem. The random forest is a decision based on the decision tree. So if we recall, our decision tree is the key component of the algorithm is to select the splitting attribute. In random forest, we will select this splitting attribute randomly. And we can generate a lot of trees, like hundreds of thousands. So there's two methods. One is random input selection, where we actually have, there is a attribute that you set. You can see at each node, I'm going to select one attribute from a set of K attributes. So that K is a parameter that we could set. In practice, people have shown that even when that K is 1, meaning we just randomly select any attribute to build the tree, the performance is equivalent. I mean, it doesn't drop the performance that much. The second approach of getting this splitting attribute is to, when you have very small number of attributes, you don't have enough attributes to generate a lot of trees. Therefore, you create new attributes by combining doing random linear combination of those randomly selected attributes to increase the number of the attributes that you could use to split the nodes and create mini trees. Again, the tree is, you have lots of tree created, then the final decision is either a vote, majority vote, or produce a probability based on all the decisions of different trees. Questions? Okay. So now we move on to another topic, which is about class imbalance problem. So earlier we talked about using ensemble methods to improve performance. Any methods could be used as the base to create an ensemble. But random forest is based on decision tree that you can't change. But boost can be used with other base algorithms. Class imbalance problem is often seen. This is the situation where our classification task involves a very rare class, but the rare class is actually is what we care. So example, medical diagnosis, maybe 1 in 100 people have this disease. So the example that we collected going to have lots of healthy people, but very, very small number of the sick people. But our goal is to identify those sick people. Terrorist attack, majority of the population are good. We just have a few people who are really extreme, and how can we find those people? Because all those vast majority of the machine learning algorithm was designed with a balanced distribution class implicitly assumed, they are not suitable for class imbalanced class classification problem. However, our evaluation metrics have been developed. For example, sensitivity plus specificity, precision recall, and the F-score allow you to weight, to put different weight for precision recall. Evaluation metrics is good to help with class imbalance problem is because you can tune the system by looking at the performance increase and decrease that really hit your needs. For example, in a class imbalance problem, we want to increase the recall of identify this positive example. We don't care much about the position. We can tolerate a lot about false positives, but we want to get lots of recall, to increase the recall. But there are also other ways to address class imbalance problem. Typical methods, oversampling. We can resample the data from positive class. The simplest resampling is just to simply sample more from positive class. You can sample with replacement, so that positive class have lots of redundant examples to increase the count. More sophisticated methods generate synthetic samples. Well-known ones are Ch8 and Improve. Ch8 generate a fixed number of examples for each minority sample. Improve generate different numbers of examples based on that conforms to the class distribution. We're going to look at Ch8 as example in our example shortly.
In this case, is the difference between boosting and oversampling is boosting just increases the probability you will sample, let's say, a misclassified example, but here you actually repeat, like not just increasing probability, you're going to make 3 or 4 copies of that?
Right. I think the boosting is an ensemble method. You have multiple classifier. You create multiple classifiers. Each of them may have balanced or imbalanced examples. If you could actually address imbalanced problem in a boosting in an ensemble setting as well. You can resample data for positive on the minority class to make the class distribution balanced. The oversampling is basically just trying to make the number of positive and negative classes equal in your training example.
So, sorry, then thank you. That I understand the difference. Boosting is for multiple classifiers. So by increasing probability, you're just increasing probability that, important sample
Right.
is going to be
You
seen
can
by
still
multiple.
get imbalanced sampling that way. That you can still apply oversampling there to get the samples more balanced.
So here, then, is it when you resample, is there now a greater risk of
Overfitting?
yes, sorry.
Very, probably not. The reason here, we have an imbalanced data problem. So we can probably think of medical diagnosis, right? So we have 200 examples. Among them, 2 are positive. If you use naive Bayesian, for example, we're going to have a difficult time to sample. We're going to have a very difficult time to estimate the probability distribution for any of the attributes. If we use decision trees, as our tree example have shown so far, every time we run decision tree, it always either predict a white or Hispanic. It never predicts Black, Asia, or other, because they just don't have a chance to show up. Because our training example have so imbalanced positive and negative examples. Here, the idea is to artificially increase the positive class. Our goal, again, is we're not concerned with the overall performance of identifying positive and negative classes. Our goal is to identify positive classes, which is the rare class. It occurs very rarely.
Thank you. So, and follow-up would be then this oversampling, for instance, it's done only during training, right?
Right. You just want to make the model pay more attention to your rare class. So they have been represented in the model. None of those methods are perfect, I tell you. It's just a way to mitigate the problem, make the problem less severe.
I have a question, if that's
Yes.
okay. So I'm thinking about if we could consider a rare class to be likely to be like a difficult class to classify, then couldn't something like boosting also solve the problem instead of oversampling?
Yes. No. So yeah. Well, so boosting, when you don't have resample, if you don't balance your data, boosting going to have the same issue. Even if we generate lots of random trees, for example, each of the tree won't have the Asia and those minority class represented. That can still be a problem. You have a better chance to address this problem, but the chance is not great.
So is fundamentally perhaps the problem here that if I have 99 negative, like healthy people and 1 cancer patient,
right?
Then you know, you're accurate. If you predict the 100, all of them as
Yes,
healthy, you're just getting 99% accuracy off the bat. So the
right.
classifier is sort of leaning towards saying, hey, everybody's healthy.
Yes. So your positive data completely obscured your negative data. The distribution of the negative data is totally not covered.
Thank you. That really clarified my question. I
Yeah.
appreciate that.
Right. No, certainly. Yes.
When data is imbalanced and we have like just a few number of samples from the positive class, even in that case, oversampling might not be helpful, right? Because if we don't have enough information from that class, we wouldn't be able to generate like good.
Exactly. Exactly. Yes. That is exactly true. So I was saying that none of those methods actually solve the problem. It's just getting the problem less severe. And also Smart and Edison that we think generate the synthetic examples generated. For example, Smart does this kind of synthetic generation. We're going to use numerical data as example. It's easier to explain using numerical data. So if you imagine that we could actually plot, do a scatter plot of those positive, negative examples on a two-dimensional space, we have very small number of negative, positive classes. This Smart will ask you for a parameter k nearest neighbor. If you give it 2, it will look at, for every minority sample, look at the 2 nearest neighbor. It will draw a line between this minority example and the 2 neighbors. It will select a random dot, random position between the current example and the neighbor. This way, it can generate 2 additional synthetic sample. Does that make sense? So the samples created are not exactly the same, but it is closer to your positive class than it is to the negative class. I hope that it actually give you additional information by generating synthetic examples. In a categorical cases like the data that we have, the neighbor is going to be determined by how many of the attributes have shared nominal values or shared categorical values, and then the neighbor that the generated example is going to again look at how for each categorical value, it's going to take the most often occurred value between the current example and the neighbors. So the synthetic example generated are going to be similar to your positive or rare class examples, not exactly the same. They could also generate some duplicates, as we're going to show later today. Okay. So undersampling, opposite, just randomly eliminate tuples from the majority class. Threshold moving is when there is a decision threshold. So for example, when we did ROC curve, we adjusted the decision threshold, the probability to classify things into positive and negative examples. This threshold moving is actually one of the pretty good method when you have severe imbalanced data. This this been proven being very effective. You don't have to do a lot of things just to lower your threshold. It is also useful when you have an imbalanced data problem in multiple class classification problem. Those are really very challenging, and no solutions has been proposed for those. And ensemble techniques that I think student already mentioned could be used. We can use ensemble methods and using the oversampling and undersampling to improve the performance. I think next week we're going to introduce another way based on ensemble technique to improve system performance.
Question on smooth. I understood the continuous data, but I was still a little bit not sure on, you said, how do we do categorical data?
I can send you a link. There is a paper. I found the original SMOTE paper. The R implementation with SMOTE is actually used a different method than the SMOTE paper. But I went back to look at SMOTE's paper, how they does the similarity. So the key idea in this method is find the nearest neighbor, right? Second step is to generate. After you find the nearest, because the synthetic example is going to be generated based on this current example and its neighbors. So the first step is to find neighbors. Second step is to generate example based on the neighbors. The main idea, the key idea, you can look at the paper in detail, but the main idea is to find, remember every observation is a vector of features, right? And features here are categorical. So the similarity between one instance or observation with another can be computed by how many the extent of the overlap of the feature values in those two vectors. So this way you can find this instance and its similar instances. This forms its neighbor. Once the neighbor is formed, then you can apply, again, the similar ideas to find the overlapping. So your new example, you need values to fill in the blanks in this new feature vector. This value can be identified by using the most often occurred attribute most often occurred value in this position from the neighbors and the current example. Anyway, I'll send you the paper. It's about a page long on the categorical data. And they actually showed that the performance on categorical data is not very good. So it's a class imbalance problem remains, binary or multi-class classification task remains a challenging topic. Okay. So I think we completed our slides, and now it's 2:12. Shall we take a break and coming back on 2:22? And then we will start to look at our R code, showing the ensemble methods and the imbalance SMOT, how to generate examples.